even light, is believed to escape. These cosmic titans are the ultimate expressions of gravitational collapse, where mass is so densely compacted that space and time are warped to extremes. Within their depths, the laws of physics as we know them seem to break down entirely. Yet, in a remarkable twist that has stunned astronomers and physicists around the world, NASA's James Webb Space Telescope has delivered an observation so extraordinary, so unanticipated that it threatens to upend our most fundamental assumptions about black hole physics. On the far side of a galaxy billions of light-years away, near a supermassive black hole that dominates its galactic core with the unchallenged authority of a gravitational monarch, Webb captured what appears to be a narrow, focused flow of material, energy, or light emerging from a region frighteningly close to or possibly even within the event horizon itself. Unlike the well-documented bipolar jets, those high-speed streams of particles driven out along the rotation axis of black holes due to intense magnetic fields in the surrounding accretion disk, this newly observed beam was not typical. It was tightly collimated, surprisingly orderly, and most shockingly, it seemed to originate much deeper in the gravitational well than current models would allow. This was not the standard messy flash of radiation or energetic jets formed just outside the event horizon, but rather disciplined, narrow column offset in orientation and unlike anything scientists had seen before. This single observation has sent shock waves through the astrophysical community, challenging decades of established thought and inviting bold new theories about the inner workings of black holes. The beam displayed a highly energetic, signal-rich spectrum that included synchrotron radiation, light emitted by magnetically accelerated particles. While synchrotron radiation itself is not unusual in astrophysical jets, the beam's coherence, sustained intensity, and apparent rhythmic pulsing implied a depth of origin and a mechanism that present theories simply cannot explain. It was not merely a question of material escaping a black hole's pull, but of the highly structured, periodic nature of its emergence, something that challenged the foundational principle of general relativity, which holds the event horizon as an absolute one-way boundary. Black holes are typically understood as cosmic death traps, regions of spacetime where swirling disks of gas and dust spiral inwards, heating to extraordinary temperatures as they fall closer to the point of no return. Occasionally, matter interacting with magnetic fields near this edge can produce spectacular twin jets, relativistic streams blasting out at nearly the speed of light. But those known jets arise from matter that has not yet crossed the event horizon. What Webb's instruments recorded was altogether different. A steady, pulsing beam whose origin appears to be in a region where, according to Einstein's equations, all information should be lost to the universe forever. Webb's powerful infrared sensitivity was critical in making this discovery. Unlike many telescopes that struggle to peer through the dense clouds of gas and dust surrounding galactic cores, Webb's instruments can cut through these veils, offering an unprecedented view of black hole environments. The data was startlingly clear. Rather than an erratic flare, Webb observed a rhythmic, nearly heartbeat-like ejection pattern, steady and deliberate. Spectral analysis confirmed that this was no mere optical illusion or imaging artifact. The beam's light carried modulated signals, as if its energy were being pumped or gated by an internal periodic process. Such regularity suggests a level of internal organization previously unimagined for black holes. Some theorists propose that the observed rhythm may be linked to the spin of the black hole or to interactions between its powerful magnetic fields and exotic quantum processes near the event horizon. Instead of a chaotic maelstrom where all order dissolves, we might be witnessing a self-regulating mechanism, a cosmic engine with internal feedback loops. This possibility flies in the face of the classic view of black holes as purely entropic endpoints, consuming matter and energy without any meaningful structure or output. This observation also touches directly on the famous black hole information paradox, one of the most vexing problems in theoretical physics. General relativity predicts that anything crossing the event horizon is lost forever, while quantum mechanics insists that information cannot be destroyed. Hawking radiation offered one possible bridge between these theories, with black holes slowly leaking energy through quantum effects at their boundary with virtual particle pairs leading to extremely weak, random emissions. But Hawking radiation is generally considered too feeble and unstructured to convey meaningful information. Webb's observation of an organized energetic beam suggests something very different, a potential mechanism for energy and perhaps even information to emerge from within the black hole in a coherent, non-random fashion. One hypothesis is that certain quantum phenomena at the event horizon could be amplified under extreme conditions. Perhaps the black hole's immense spin, intense magnetic fields, or the presence of exotic matter could enable these quantum effects to become coordinated, acting as a kind of quantum engine that channels energy in a structured way. Another, more speculative, possibility is that the beam consists of exotic particles such as actions or other weakly interacting particles proposed by theories beyond the standard model of particle physics. If these particles exist and can escape even the extreme gravity inside the event horizon, Webb may have provided the first observational evidence for dark matter-like entities being expelled from a black hole. Such a discovery would not only revolutionize astrophysics but also transform our understanding of particle physics, offering new clues about the elusive nature of dark matter, a component thought to make up most of the universe's mass, yet which remains invisible and poorly understood. The very formation and alignment of the beam add further mystery. Traditional black hole jets align cleanly with the rotation axis shaped by the black hole's magnetic fields. This newly observed jet, however, breaks that rule, emerging at a clear offset. This irregularity might suggest an underlying asymmetry in the black hole itself or even hint at more exotic geometries in spacetime, such as higher dimensional structures. Some theorists have even revisited the tantalizing idea of wormholes, bridges through spacetime connecting different regions or even different universes. While wormholes remain speculative, the observed, long-lived, and organized nature of this jet gives such concepts a new degree of plausibility. If this beam represents the visible end of a cosmic tunnel, it could be the first observational evidence of such a structure, shifting it from theoretical possibility into the realm of empirical science. The periodic behavior of the beam implies there is a feedback process deep within the black hole structure, potentially tied to its spin dynamics, quantum fluctuations at the event horizon, or other unseen interactions. Instead of seeing black holes purely as destructive endpoints, this discovery raises the possibility that they are complex, dynamic systems capable of self-regulation. They might breathe, expelling energy in a rhythmic cycle that balances the infall of matter with controlled outflows. Such a model suggests black holes could play an even more active role in galactic evolution than previously thought, not merely swallowing matter, but also influencing star formation, galaxy dynamics, and the broader distribution of matter and energy in the universe. This observation also intensifies the debate around the black hole information paradox. For decades, physicists have argued over whether information swallowed by a black hole is truly lost, a possibility that would violate fundamental principles of quantum mechanics. If Webb's observation demonstrates that information, however transformed, can emerge from within a black hole, it could be the key to resolving one of the greatest puzzles in physics. It would suggest that black holes are not simply cosmic trash compactors, but might store, process, and even share information with the wider universe in ways we are only beginning to imagine. In this light, black holes take on a profoundly different character. Rather than being silent endpoints in the cosmic drama, they could be seen as active participants in shaping the evolution of galaxies, seeding new structures, and perhaps even playing a role in the conditions necessary for life. They may act as both destroyers and creators, recycling matter and energy in intricate ways. The timing of this discovery is equally important. The James Webb Space Telescope is just beginning to realize its full potential, already revealing hidden galaxies, ancient stars, and now perhaps the first hints of a phenomenon that could reshape not only astrophysics but our fundamental understanding of the universe itself. Webb's instruments have not only captured the shape and path of the beam, but also allowed scientists to analyze its composition and speed with astonishing precision. The beam moved at nearly the speed of light but showed subtle energy variations, suggesting it might contain mass-bearing particles rather than being purely made of photons. If this is true, black holes could be the universe's most extreme natural particle accelerators, capable of probing physics far beyond the reach of even our most advanced Earth-based colliders like CERN. The steady, rhythmic nature of the beam hints at a kind of natural intelligence, not conscious in any human sense, but reflecting the self-organizing complexity found in many physical systems. It suggests that the black hole's spin, magnetic fields, and quantum boundaries might interact in feedback cycles that modulate its behavior in patterned, even predictable ways. This leads to the revolutionary idea that black holes are not mindless voids, but finely tuned cosmic engines, machines that regulate, organize, and redistribute energy, and perhaps even information across the universe. The James Webb Space Telescope may have captured more than just a strange new jet. It may have offered the first evidence that black holes are storytellers, cosmic archivists who record and share the universe's secrets in ways we are only beginning to decipher. And now, for the first time, we are learning to listen to them. The implications of this discovery ripple outward far beyond astrophysics, touching fundamental questions about the nature of reality itself. If black holes can, under certain conditions, act as engines of energy and information release, they may represent a bridge between general relativity and quantum mechanics, the two great but famously incompatible pillars of modern physics. For decades, scientists have struggled to develop a theory of quantum gravity